Okay, here we go. Today we want to examine the graphs of polynomials. This is going to be our intro to the fundamental theorem of algebra. It's a beautiful thing. I think the coolest part of algebra. And we begin with looking at their graphs. So, for example, if we have a first degree polynomial, say y equals x, everybody knows that that just makes a line. Whereas if we have a second degree, what shape does that make? Makes a parabola. So this is a single sheet. You're going to go to the back side of that single sheet I handed to you. Okay, a third degree, or y equals x cubed, I'm going to draw a little bit differently than we've seen it, just as it has a couple kind of bumps in there. Okay. Then y equals x to the fourth, which kind of look kind of like a W. Everybody see a pattern developing? Add more bumps. There you go. Yeah. Natalie, you're going to say, okay. All right, so there's some observations that we're going to make, and I want you to know that you don't have to remember everything that we put together here, but this is going to help us go deep in our understanding of what's happening with the graphs. Okay. We're talking about local extrema. Extreme values are the largest or smallest within an immediate area, within an immediate region of each other. So how many local extrema does this have? One. Yeah. Just has one minimum. How many does this have? Two. How about this one? This one? So, and this one has none. So, given a polynomial of degree n, there are at most how many extrema? N minus 1 extrema. An extreme value is going to be a value that is larger or smaller than any of the other values immediately around it. Okay? Now, it might sound like a tough definition to say, what does immediately mean? Well, let's not get too technical, but if I were to give a precise definition, I don't think we really like it too much. So, just if you kind of make a small window around it, it's bigger than all the other values right around. Okay. All right. Well, this one has 4. This one has 3. This one has 2. So we're just taking the degree minus 1, and that's how many local extrema could have. At most, because you guys also learned that a cubic could also look like that, right? And that has no extrema. That is none. You also learned that a fourth degree could look something like this, right? That has one extreme value. So just because it's fourth degree doesn't mean it's going to have 3 extreme values. It might just have 1. Okay, it has at most n minus 1. Okay, let's now consider the shapes. Okay, and let's consider this, what we call this end behavior of the graph. And I don't want to think about as x goes towards negative infinity or the left side of the graph. Right now, I want to focus on the right side of the graph. What do you notice about all these graphs about the right side of them? Where are the graphs headed towards? They're headed up. As long as the graphs are positive, as x goes towards infinity, the y values go towards infinity as well. And that should make sense. If you take a positive number and square it, or a positive number to the third power, or a positive number to the fourth power, they're just going to become bigger values, right? And so therefore, as long as we have a positive value, it doesn't matter whether we have an even degree or an odd degree, as x goes towards infinity, y goes towards infinity. So it ends going up. That's the idea. Draw an arrow for up. Okay? All right, let's consider if they're negative. If they're negative, they're going to be, just flipped upside down. So I'll draw the negative ones in red. If you want to draw them, you can, but you don't have to. You can see from what I'm drawing here. What do you notice about how all of these end their behavior? They all end their behavior going down. So if it's negative, doesn't matter whether the degree is odd or even, y will go towards negative infinity. Now let's consider how it starts. Please start by looking at the green functions. Don't look at the red. What do you notice about the green functions and how they start? Do they all start down? They start lower than they end if you're odd, right? But if you're even, like look at it. The even functions, they start and end in the same direction, don't they? Yeah. Let's think about y, okay? If you take a positive and square it, you get a, if you take a negative and square it, you get a, see that? But if you take a negative and cube it, you get a positive. I'm sorry. I said it incorrectly. You answered correctly, okay? So if you take a positive and cube it, you get a positive. If you take a negative and cube it, you get a negative. So the odd ones start and end in opposite scenarios, whereas the even ones start and end in the same directions, okay? So let's look at the odds. If it's odd, that means it starts in the opposite direction. So y goes towards negative infinity. And again, it's odd, so it's going to start in the opposite direction. So now it's going to start up. So y goes towards positive infinity. But if they're even, then they start and end the same. So if it ends going towards positive infinity, it will start going towards positive infinity. And if it ends going towards negative infinity, it will start going towards negative infinity. Now, you don't have to memorize that chart. What you do need to keep in mind is this. If it's positive, it ends going up. If it's negative, it ends going down. If it's even, it starts the same as it ends. If it's odd, it starts opposite of how it ends. That's the line of logic, and we'll work through that, and trust me, you'll be able to figure it out. The last thing we need to think about is our single, double, and triple roots, okay? And so single roots and double roots and triple roots, here's what they look like. A single root just passes right through the x-axis. A double root actually bounces off of the x-axis. A triple root slows down and kind of flattens out as it passes through the x-axis. I'll write an example here, say x minus 1. It's called a root or a 0. What would you plug in to make 0 there? 1. Whereas here, x minus 1 squared, you would plug in 1, but how many times can you plug in 1? Plug it in twice, right? Because it's x minus 1 times x minus 1. So that would be a double root. 1 happens twice. Whereas here, x minus 1 to the third, that happens 3 times. You can see that we have 1, 2, 3, 4 spots where the graph crosses 0. One of these is a single root. Which spot is a single root? 4 is a single root. One of these is a double root. 1 is a double root. And the other 2 are triple roots. One thing that I really like about this is you can actually now write an equation for this graph. It's like, what is the equation for that graph? Looks ridiculous, doesn't it? It's no big deal. X plus 2 would have a 0 of negative 2, right? And it's a triple root. X minus 1, because 1 is a solution, correct? And it is a double root. X minus 4 is a single root. And x minus 7, that would be a triple root. And if I type it into my calculator, just as so, and I press graph, I have to adjust the window a little bit, but in seconds, I've created the exact visual of what we saw there. It's part of the fundamental theorem of algebra. So you may wonder, how can you create some of these shapes? Pretty straightforward. Create whatever shape you want to see. Okay? All right. That is your graphic organizer. You want to keep that handy. Now flip to your notes, this front part. We look at polynomials and their graphs. These are all factored in form, okay? We first like to identify the degree. This is how I do it. If you have a different way, that's absolutely fine. I just find this to be most efficient for my use. What's the degree of this polynomial? If I were to multiply it out, I would get an x squared, so second degree. Positive or negative? If you multiplied it out, would you get a positive x squared or a negative x squared? Positive x squared. Well, if it's positive, that means it ends going up. And if it's even, then it ends and starts in the same direction. So I just took you through the general logic that I think about when I think about these graphs. Now, when I first started teaching it, I would tell people to think about where it starts. It just seems natural to think about where it starts, right? But it actually is better to think about where it ends, right? Yeah, so anyway. Sometimes I feel bad for the kids I taught early on. I wonder if I actually confused them more than I helped them. So it crosses through those two spots. We know it starts up, we know it ends up, and we will just draw single roots in between. And then, no surprise, that's a parabola. Basic example done. Good to go? Okay. Let's make some headway here. Degree. Degree, positive or negative? Negative. So it's going to end, down, start. Why does it start up? It's odd, so it's opposite. Okay? Yep, exactly. Third degree. So I have solutions of -4, 1, and 5. Okay. Starts up, finishes down, and they are all single roots. No. Okay. See, that's negative. If it's negative, it must finish down. Doesn't matter whether it's an even degree or an odd degree. If it's negative, it finishes down. Trust me there? Okay, then we have to consider where it starts. If it's odd, it starts opposite of where it finishes. If it's even, it starts in the same direction it finishes. See if the next one connects. If not, ask the question again. Okay, degree 3, positive or negative? So it finishes up. Now that we've established it finishes up, we look at the degree opposite. Very good. Okay, so I have positive 1, 0, and negative 5. Starts down, finishes up. Some of your graphs will be difficult to read. I'll do my best. So I was looking at the last test. What was very challenging for me to read for some people was your infinity symbols. The number 8 looks like that, whereas the number infinity looks like that. Excuse me, it's not a number, it's an idea, but infinity looks like that. So actually some people I saw you like wrote like the letter G for like a G, like the function G, and I really started to struggle to understand what was what. So if I made some notes on your test when you get it back, don't feel bad. I'm just trying to help you understand. I don't know what you're doing. Okay, next one, degree. It is a third degree, positive or negative. So it's going to finish, start. So just making this little kind of note here, this organizer seems to help us kind of work through our logic. I'm going to plot negative 4. I'm going to plot 0. So what happens at negative 4? Why, Olivia? Lover of mathematics? Yes, you are. Because it's a double root, right? Negative 4 happens twice. Yes. Nope, I don't know what if we're going to do the graphing thing with the what. I don't know. Sorry. I don't know what you're talking about. No, I'm like. Oh, excellent. No. All right. No, not even close. So, but which part? No, it's not. It's supposed to bounce off of negative 4 because if you consider our double root, look back at this, your double roots have this type of behavior. It touches and it bounces off. It does not pass all the way through. Just like think about double and quadratic. A parabola, that's the shape it's going to have at that 0. We're not going to test on that, but without a doubt, I would expect that you could extend it to that type of situation. Okay? All right. Flip it over. Do a few more here. What degree is number 5? It is a fourth degree, positive or negative. Because if you were to multiply it out, you would get a negative x to the 4th. Very good. Very good. Now, so it's going to finish down and starts down because it's even. Very good. It would finish up, it would start up because, it would finish up because it would be positive, but it would start up because it was the 4th degree and they start and end in the same spots. See, so because it's even, those are the same. If they're odd, then these are different. This matches with that. Negative goes down. Then because it's even, these are the same. Okay? All right. So I'm going to plot negative 3, negative 5, positive 3, positive 5. Some people wondered, this is a negative 3 here. They wondered, should that be a negative 3 there as well? And the answer is no. You have to consider what do you plug in to make 0? Okay? These are all single roots. No, I said some people want to say that that's -3 as well, but it's not. You have to consider what do you plug in to make 0. We'll do 3 more, 6, 7, and 8. What is the degree for number 6? It is 5th degree. Positive or negative? Positive. So it will finish and it will start down. What kind of root do I have at 0? It's a triple root. I'm going to put a T for triple. What kind of root do I have at 4? A duple. Very good. Yep. Wow, we're going downhill quick. So, question? It starts down. Do you see why it ends up? Because it's positive, it ends up. We good there? And then because it's odd, it's opposite. Now, so if you draw that in place, okay, then you got to kind of, this middle behavior is what we actually call it the hidden behavior of the function. What does it do in between? And calculus exhausts a lot of time in order to figure out exactly what this behavior looks like. We're able to give a kind of a nice description, but it's not perfect. But this triple root here, we know that it goes like that, right? And it goes up. We don't know how high it goes. And I'm not gonna judge you on the accuracy of that bump, okay? But in calculus, we actually can find how high that middle bump goes, which is pretty cool. So we don't know what that is, but that's the idea. Now, here's what people do that's incorrect. I want to be clear. So when people draw their triple roots, here's what they do sometimes. So I'll draw in green. So they would do that. And so instead of having it flatten out horizontally, they have it flatten out vertically. That is not the behavior. Yes. Oh, it just crosses once. It is, if I try to draw it, a little kind of a softer version, it just flattens out for an instant. I mean, just it doesn't stay flat for a certain period of time. It's flat for just one point. You know what I mean? I'll tell you exactly. This will answer it. For a single root, it has, say, like a slope of 2 or 3 as it passes through. For a triple root, the slope right there is 0. It flattens out. So I'm going to say it flattens out. That's what it does. Okay. All right. And again, I'm not going to try to be too critical, but you need to try to show a little bit of that behavior when you do your graphs. Okay, degree here. 2 more. Fourth, positive or negative? Negative, finishes down, starts down. Good. So I have zeros at 5, 2, and -1. I start down and I finish down. What do I have to keep in mind? Double root where? It's at -1. So why would you be tempted to put the double root in the middle? Because the -1 sits in the middle of the other two. I mean, conceptually, that's what you're thinking about. Just make sure, so I sometimes encourage people maybe put a D by where it actually is a double root. Single roots. A single root, it would have actually crossed the x-axis. If you had a single root here, you would do this. Okay? Better? All right, last one. You try the last one on your own. This is what your graph should look like. It's negative, so it finishes down. It's an odd degree, 5th degree, so it will start opposite of where it finishes. It has solutions of -2, +4, has a triple root at 0. And so that's the behavior that you get. Good question. So we know we have that, right? And we know we have that, right? Now, it's hard for me to give an exact way to fill the middle in. But I can tell you this. Do you have a single root or double root here? Single. So you know you're going to have to do that, right? Do you have a single root or double root here? Single. So you know you're going to be like that, right? So now you got to somehow get from here to here by showing a triple root. And yeah. It's kind of like a puzzle you got to piece together. Here's your assignment, okay? I cut down the assignment by about 6 problems from last year to take into account your other stuff. I'm also redoing a lot of the assignments you have for this unit in order to make room for your spiral review, because your spiral review is going to be very important for your final exam. Now, this looks like a lengthy assignment, but trust me, I could make the assignment look shorter, but it wouldn't actually be shorter, right? Like, it's nice and short as it's written, but it's not shorter, is it? So, okay. So here you go. These these are already factored. These need factoring. So all the ones we did in class were already factored for you. But this will be a good review of your factoring needs, okay? As we move along. Next couple days, we're going to be doing some synthetic division. Maybe you remember synthetic division. Good times. We're going to be doing some factoring. We're going to get to something called the rational roots theorem. Good stuff. Shout out to Anna. Anna, we miss you. Kenzie, stop laughing. Kenzie, we don't think it's funny that Anna's sick. Okay, I'm sorry, Anna. It's kind of took a turn here for the negative. So, tell you what, Anna, if you show up tomorrow and you say the keyword Archimedes, you say Archimedes, I'll get you a zebra cake or something. Nobody tell her. We'll just see if she actually watches the video.